So that's my motivational speech when it comes to statistics. Yeah. It's not the most boring course, though. Promise you that. History of math. Take that class. You haven't experienced boredom yet. So anyway, the probability distribution is the extension of what we were talking about. It's the idea that not only can you find the probability of a single event occurring, you can find the probability of every possible event occurring. And then make a list and create a graph. And look at the graph and enjoy the graph and stuff. No, it really does give you a true sense of what's going on in a more holistic sense, because when you're dealing with just probability of getting red, all right, okay, what does that mean? But when you apply it to other situations, you can kind of look at it and say, well, the little fluctuations, the minute fluctuations from one variable to another can give you more of an understanding of what's truly going on. I kind of look at it like I make up names for things. I call it the penny stock situation. It's like lots of little fluctuations in stock prices, as opposed to like a mutual fund, which is steady growth or decline. But really, it's just more of a gradual thing. But those penny stocks, where people they either get really rich or really poor by lunchtime on a daily basis, that's what we're really looking at when we're exploring a probability distribution. Those little fluctuations can give you a lot of insight of what's going on inside a data set. And like going back to games of chance, it really does give you a leg up if you have a good understanding of that. And of course, baseball. If you've ever wondered why, if you do like baseball, if you've ever wondered why on, let's say, some random Tuesday, your favorite second baseman who you went to see, you bought the ticket especially to see him, then you get there and he's like, oh, he's not playing. And you're like, why is he not playing? And they say, because it's his day off. I didn't know they got days off. Okay, well that sucks. I mean, tickets cost me $400, but he got a day off. It happens. The pitching matchup, that slight edge to the pitcher, is what dictated that player not playing that day, because the numbers for the backup second baseman that are ordinarily terrible just so happen to be astronomical against that one individual. So that one little spike in his probability of success dictated that individual plays on that day. Right? So that's the power of the probability distribution. But we can't start with that, so we start with something much simpler. Probability distribution for one roll of a fair die. Well, there are 6 possible outcomes. The numbers 1, 2, 3, 4, 5, and 6. Now, the probability of success here is the probability of getting any of these outcomes. There's 1, 1, and 6 sides. There's 1, 2, and 6 sides. There's 1, 3. There's 1, 4. There's 1, 5. And there's 1, 6. All right? That is a probability distribution. So it can be very easy. The little caveat here is that you have to account for all possible outcomes. The way to verify that that's happening is to first make sure that each of your probabilities are between 0 and 1. Right? They have to follow the rules of probability on an individual level. Right? So if I get a negative probability, that's not going to work. If I get a probability that's greater than 1, well, it's not a probability. Right? It's got to be between 0 and 1 inclusive. Also, if I'm accounting for all possible outcomes, the sum of those probabilities should be equal to 1. All right, so the sum of my p of x values should be equal to 1. It's a little early in the game for you to have looked at the review problem set for the next unit test, or practice exams for the next unit test. But if you did, you'd see a problem very much like this. I always put a problem like this. Determine whether the following is a probability distribution. And if so, find the mean and standard deviation. It's the kind of situation where you're rooting for the answer to be no, it's not a probability distribution, so that you don't have to do the work. Right? Fun fact, it's almost never a probability distribution, but 75% of the class is still going to find the mean and standard deviation. Right? Because it's just a force of habit. We're not looking to find a mean and standard deviation of something that doesn't fit the definition of a probability distribution. What am I finding the mean and standard deviation of? Nothing meaningful, I'll tell you that. So now that I know it's a probability distribution, though, I can find the mean and standard deviation. I can do it in the calculator, but just this once, and this will be the last thing we do today if you're concerned about that sort of thing. Just this once, I want to do it by hand, just so you get a feel for the similarities and differences between this kind of standard deviation and some other standard deviations, like the sample standard deviations from the last unit. Right. So in order to find the mean, first thing we do is we find the product of x and p of x. So 1 over 6, 2 over 6, 3 over 6. Don't reduce your fractions. You'll regret it. It won't be like a lifelong regret. It'll be one of those like momentary regrets. But it's still a regret. So what we're coming up with here is essentially a weighted average, right? Because basically what this is saying is that if we're assuming that the value of the side has meaning, like 2 is twice as valuable as 1, 3 is 3 times as valuable as 1, and so on, then we're weighing each of these values based off their probabilities. That generally is not the case when we're talking about a roll of a die, but it could be. You know, depending on how the game is valued. You know, you play the game of craps, 2 is not twice as valuable as a 1, but getting a sum of 7 when you roll 2 dice is more meaningful than getting a sum of, let's say, 3. So there are games in which the type of outcome is just as important as what the outcome is individually. Right? So what I want to do here is take the sum of all those weighted values. Sum of x times p of x. And what we're going to get is 21 over 6, if memory serves, from the last 100 times I did this problem. And that's going to be mu. All right, so that mu, very important. So it's in the little formula section below. That mu stands for the population mean. And a population accounts for every element that makes up a set. So if I was talking about, just keeping it simple, population of the human race, it would be every single human that makes up the human race, all right, without exception. Here, it's a population mean as opposed to a sample mean because we are taking into account every possible outcome when you roll a die, all right, every single one of them. Nothing has been excluded, all right. It's not a probability distribution unless you've accounted for every possible outcome. And the way we know that we've accounted for every possible outcome is the sum of our probabilities is equal to 1. 1 representing 100%. 100% meaning all of whatever the item is. All right. The other thing that we have here is the population standard deviation. All right, so population standard deviation. So instead of the sample standard deviation, we have the population standard deviation. Rationale being the same thing. All right, so we have the entirety, really, of outcomes. Every possible outcome has been included. So we have 100% of the population, so therefore it's a population standard deviation. It's not a subset of the population. All right. So we'll compute that in a second. It's really no more challenging. It's just a few more ingredients. A little bit more calculator work, but nothing too crazy. The good thing is, if you are comfortable with things like the empirical rule and usual versus unusual values from the last unit, there's no difference in those relationships. All right? The mean plus or minus 2 times the standard deviation. It works the same way for samples as it does for populations. All right? So you can kind of rely on that past knowledge. So, we're just kind of tweaking it a little bit. But really, there's no more to it than that. As far as coming up with these values, like I said, a couple more ingredients come into play, but part of it is the mu squared. So that mu squared, I see a 3.5. I don't like the looks of that for mu. If I'm going to square a decimal, I guess it's fine, but that means I'm going to be working with decimals. Let's make that 7/2. And then off on the side here, I'm just going to write mu squared is equal to 49/4. All right, and just so I can say I said it, mu, the Greek letter mu, because some folks are like, what does he keep saying? Is it u or is it, I don't even know. It's like M-Y-O-U, mu. Right? It's a weird term. We don't use it very often, but all right. So that's really what it is. In terms of actually creating the letter, it's really just kind of a hybrid between the letter M and the letter U. So just kind of make your M have a little U flair to it, and you'll be fine. What some people do, just because they penmanship is not one of my strong suits. If you make an M, but then kind of extend the right end of it, I'll know what you mean. All right, so just so you don't have to worry about that part of the notation. I only bring this up because these are the things that have given people stress over the years, and I just figure there's enough other things to be stressed out about. It does not need to be one of them. So x squared. So when I'm computing my sigma, I need x squared multiplied by p of x. But Rome wasn't built in a day. So let's find x squared. 1, 4, 9, 16, 25, 36. Then we'll multiply that by our p of x values. And the idea here is that, don't resort to decimals until you have to. And even then, resist the urge. All right? Because odds are your unreduced fraction is going to be the way to go. So I'm multiplying 1 by 1/6, so 1/6, 4/6, 9/6, 16/6, 25/6, and so on. The sum of these values. So we're looking at, sorry.
sum of x squared times p of x. My pen is being difficult. There we are. So here we could just take the numerators like we did before when we were finding the mean and just add them up. So over 6. Oh boy. Spiraling out of control here. Just going to do a quick double check on that. One, 4, 9, 16, 25, 36. That's 91. I think I was just hoping. Alright, and so now it's the sum of x squared times p of x minus mu squared. Alright, so for that, we're going to do the 91 over 6 minus, was it 49 over 4? So alpha y equals 91 over 6 minus alpha y equals 49 over 4. And we are looking at 35 over 12. So we get sigma is going to be equal to the square root of that. Alright, so square root of that is going to give us approximately, I don't understand why that keeps happening, approximately 1.708. Alright, so next class I'll talk about first where that formula came from, because it's closely related to the standard deviation formula from the first unit, and also how we could avoid doing all of this by putting it in our calculator. And you'll see just how easy it is. All right, so that's where I'm going to leave it. It's very simple because it's exactly the same as the graph and calculator approach from the first unit. All right, so I have an x and a p of x. X is the individual value, so we store those values in L1. P of x serves as our frequencies. They're relative frequencies, but they're still the same concept. All right, so those values go in L2. All right, so stat, edit. I have some stuff from another class in here, and I'm going to regret clearing those out because I need them for tomorrow in that class, but whatever. I'm going to type in the numbers 1, 2, 3, 4, 5, 6. This, what I'm about to do is completely optional on your part. You could type in 1 divided by 6 times. I personally, anytime I can employ one of my best traits, I consider it laziness for a purpose. Right? The idea is, like, you have to work at being as lazy as I am. Right? So it takes a lot of effort to be this lazy. I really don't want to type in 1 over 6 times. What I would rather type in is 0 times L1 plus 1/6 right on that L2. All right, so you go up onto the column heading L2 and hit enter, and you get that blinking cursor at the bottom of the screen that says L2 equals. What this allows us to do is write a rule for the entire column. And when you do that, what it's going to do is take each entry in L1, multiply it by 0, and you're like, well, that just made it 0. What did that do?
but then 0 plus 1/6 is going to give you 1/6. What it guarantees is that for each number that you wrote or typed into L1, it'll pair it with a corresponding 1/6. This is the height of laziness, because I develop a technique simply for this one very particular type of problem. Right? It's like, really, you can type in 1/6 6 times, it's not a big deal. But I kind of look at it. What's that?
Automatically converts it to a decimal.
That's fine. Mine's going to do that too. You could also consider a situation where you have to type in, instead of from 1 to 6, 1 to 100, and instead of 1/6 in the second column, you'd have to type in 1/100, 100 times. In that context, you're like, yeah, definitely I'm doing it this way. Right? But when you hit enter, one of two things are going to happen. Either that, or you're going to get a nice juicy error message. Right? If that happens, it's because you tried typing it in the wrong spot. You don't want to type it in the first cell of L2. You want to go right on to the column heading. Just like when you're clearing a column, you want to go right up to the column heading, hit enter. That allows you to apply an entire rule. Right? And when I go through this, I'll show you how we could have gone through the entire approach, this table approach, using the calculator also. Let it do the work for you. All right. So once you have that information in, this is a far cry from the first class where it was like, all right, we turn the calculator on by using the on key, we turn it off by hitting second followed by on. We're making strides here. So hopefully at the end of the course you'll be like, oh, okay, maybe I'm not going to treasure this thing for the rest of my life, this calculator, but I got some use out of it. All right, stat, calc, option 1, L1 in your list, L2 in your frequency list. All right, because regardless of whether it's an ordinary frequency list or a relative frequency list or a cumulative frequency list, it's still a frequency list. Calculate. And we have everything we need here. Yours would, in most cases, wouldn't say domain in SX. It's just blank, right? Okay, that's good. Because in the first unit, we had two types of standard deviation. We had the sample standard deviation and the population standard deviation. All right? Here, the calculator is saying you don't need the sample standard deviation. It's not relevant. Right? It's not really saying that, but that's what we're going to take out of it. Right? It's kind of like taking the guesswork away from it. We need mu, which is, that weird symbol, the Greek symbol that represents the population mean. Now, the calculator doesn't distinguish x bar from mu. Right? So this is how it's giving us the mu, 3.5. But it gives us sigma, the population standard deviation, directly. And you can see how, well, you will in a sec, you can see how that's the exact same value that I got over here. Or, well, I didn't show the unrounded value, but it's the rounded value, so it's the same thing. The real reason why it doesn't give you an SX value in your calculator, and for me it gives me a domain, is because the denominator of a sample standard deviation formula is n minus 1. Okay? And so n is equal to 1. 1 minus 1 is equal to 0. If it applies that formula, it's getting 0 in the bottom of a fraction. 0 in the bottom of a fraction means undefined. Right? So it can't possibly compute sample standard deviation, but it can very easily compute population standard deviation. So there we have it. All right? But let me show you how we could have done all of this stuff here. It's just basically this entire table using the table features in your calculator. Right. It's not going to be a requirement at this point, but there are some topics later on in the course where we're going to have to become familiar enough with how the table functions work that, it's not too soon to get started learning about these different functions. All right. So x times p of x
Well, x is L1, p of x is L2, so that's really saying L1 times L2. So on L3, so put your cursor right up onto L3, hit enter, you'll get the blinking cursor at the bottom of your screen. You just type in L1 times L2. Now it goes into decimal form, but it'll give you a more accurate decimal form than you'd ever come up with with pencil and paper. So that's my x times p of x column. So if I wanted a sum, right? Because I want the sum of, that's not a highlighter, geez. The sum of x times p of x. What I would do is I would actually quit out of here. It's the second mode. To get this calculation, I would use the sum function. All that information was stored in L3. So the big question would be, okay, well, where do you get the sum function? Any operation that you want to perform on a list would be in the list menu. All right, so that's second stat. All right, second stat. You just got to hunt around for it in most cases, but you have the first column is your names list. All right, that's every list that you have stored in your stat edit menu. But if you go over to ops, so right arrow to ops, you see some more options. But if you go over to math, you see the one that we're looking for is option 5. All right, so what I can do is second stat math 5. And then call up L3, hit enter, and what it's going to do is it's just going to add up the entries in L3, right? Because L3 is where I put all the values that were the product of the entries in L1 and L2. And so I get my 3.5, so that would be my mean, all right? So it's not too crazy to do something like that by hand, but there are some situations where you're like, I don't want to do it by hand. I don't want to have to worry about fractions. I don't want to have to worry about rounding. There's a lot of things you don't want to have to worry about, but time, yeah. So this is, it's taken care of for you, all right? So stat, edit, into L4, we have x squared. So that calculation, that's my x values, which are stored in L1 squared. So go on to your L4, hit enter to bring it to the bottom of the screen, hit L1, and then square that value. All right. A couple of ways to square a number. You could use the x squared key, but that'll only allow you to square things. The caret key is the way to go, which is the key right above the division key. It brings up really any power, but on mine it looks like a caret. I don't know how it looks like on yours, but usually it looks like just an elevated exponent. All right, but type in the 2 and hit enter, and it'll square each of the entries in L1. All right. Now, again, with only 6 entries, it's not crazy to do it by hand, but the same thing we said for finding the mean and all that stuff. It'll at least take care of that part for you. All right. X squared p of x. The p of x are the L2 values. All right. So I'm living in right here. This is L4. So what I want to do is multiply x squared by p of x. I want to multiply the elements from my L2 column by my elements from L4. All right. And so that'll all go in L5. So L2, and multiplication is commutative, so you could do it in either order. L2 times L4. I hit the wrong key. So you have those entries. Now, again, decimal form, so you just kind of live with it. But 1.5, for example, the third entry down, Like that's 3/2. If you look at what we got when we did it by hand, it was 9/6, which actually reduces to 3/2. So, you just look for a comfortable looking decimal, like 0.167 or 1/6 repeated. You might recognize that as 1/6. I don't know. But, just look for something that looks reasonably similar to what it looks like in fraction form. All right. The next step in the process was to take this column and add it all up. So again, second, stat, math, so over to math, option 5. All that information was in the column L5. So that's what we're going to do, sum of all the values in L5. And so now we have this entry, which is in its most exact decimal form. All right. Now, it won't convert it automatically to fraction form, but you may not need it in fraction form. But what this would be is like, so imagine you had a fractional value like, 1/3, something simple. And just to show some work on paper, you wrote down 0.33. But in your calculator, you had the full-blown decimal. You're writing down 0.33 just as kind of like a placeholder in your work, but you know that in your calculator, you're really truly working with the most accurate form of that decimal. That's really what's happening here. Along the way, you could write down rounded forms of these numbers, but in the end, we have the most accurate form of that decimal to the point where if I hit math frac, it's going to convert it over into fraction form. All right. So it held on to the most accurate form of those fractional values. When I typed it in, when I typed in that 1/6, it held on in its memory. It held on to the 1/6. It only displayed the ugly decimals because that's in the stat editor. That's the only way it knows how to display information, right? But it held on to those actual values. So we have that 91/6. And the rest of the way, you can work with it in decimal form, or you could work with it in this form. So for example, let's say I wanted it in the decimal form until further down the line. I could still keep that decimal, subtract, so the next step in the process is 49/4. I get that decimal, so I can math frac that. Math, option 1 is frac. It converts it over, all right? But maybe I never want it to be in fraction form because I know the calculator storing the best possible decimal approximation of this number. So even when I get to this ugly decimal of 35/12 in decimal form, I can just do the square root of that number. And it's going to give us the most accurate form of the answer. You're not going to lose any accuracy due to rounding. All because you let the calculator hold on to the previous values as you went. Okay, so at this point, it's a luxury, but it could be, it definitely will be a necessity down the line. You can find instances in different classes, definitely, where you might find use of this. Historically, every time I teach stat, there's a good segment of the population is like, other math classes, you kidding? This is it for me. I'm never taking a math class again for the rest of my life when I'm done with this one. And then there's other folks that are like, yeah, math, huh? I'm just starting the journey. I got years ahead of me, so, and obviously everybody else kind of falls somewhere in between, right? So what I look at the stat editor on the calculator as is Excel light, right? It's Excel light in some areas and Excel plus in other areas because it does all the statistical things we need it to do, but obviously there's a limit to how many sets of data that you could put in and how much information per set of data you could put in, right? So, and Excel, I mean, it's great because you find a data set online, you could just import it into Excel and have it do it where you don't have to type in anything. Or if you have the right data collection equipment, and I have some at the high school where I just plug it into the computer. I have a It's not a radar. It does detect velocity, and so I pointed at an object, but like a cop's radar gun. Like I pointed at an object, and not only does it detect its speed in real time, it'll import all that information into Excel for me, so I can analyze it. So that's something Excel can do. Calculators to some extent can, but if you start to familiarize yourself with that, you'll find that learning software like Excel can be a whole lot easier. All right. So anyway, that's my little spiel on that. One of the tech assignments that we're going to do is going to involve, we'll use Google Sheets because it's the free version of Excel, but if you have any experience with Google Sheets, it's in a lot of ways Excel Lite also. So but the language is very much the same. So we'll get a sense of how this stuff kind of plays out on a more expensive level. But in terms of creating a graph, so by the way, that there's a couple of different ways to verify the answers that we got by hand. Right? How it plays out on graph is dependent on your probability distribution table. Right? So it's just a matter of graphing your table, and it's pretty easy. There are two different types of variables that we have to be mindful of: the discrete random variable and the continuous random variable. Unfortunately, and this is one of those situations. I mean, I like math, but I don't like every decision that goes into all the concepts in math, and like it's one of those, like, if I ever got a hold of the people who came up with these terms, I'd wring their neck, because it's like discrete random variable. Random variable is made up of countable values. All right, cool. Could you have picked a term for it that did a better job of, perhaps giving you a sense of what the word's definition is? There's nothing about the word discrete that would make you think countable. And then continuous. I mean, you think of the word continuous, I guarantee you, if I gave you 10 chances to come up with the definition I was looking for involving continuous, you're probably not coming up with this definition, but you're definitely not coming up with the real one, which talks about having to use a measuring device to determine the value. Right? So continuous data, for example, length of a person's foot, the amount of time it takes to cross the street, right? The wattage used, that's right, kilowatt hours is what I could just oversimplify things, but energy usage in the household, all things that you need a measuring device in order to determine the value of. Right? You could ballpark it. Like if you saw somebody's foot, you could say, all right, yeah, that looks like 8 inches, 12 inches, something like that. But to determine its true value, you would need a measuring device. And the more accurate the measuring device, the more accurate your results are going to be. Right? So I think that stuff is pretty obvious. Why that's called continuous, it has nothing to do with this course. It actually has to do with calculus. Right? So continuous data has to do with something called a continuous function. Right? So, and continuous function in a function-related course, whether it's college algebra or trig or pre-calculus of whatever level, even that doesn't mean what you would think the word continuous means, because you can't help but see the word continue in there. Like it continues on and on and on. That's not what continuous means. All right, continuous means that it's a smooth curve that goes from one value to another without interruption. All right, that's a very basic rudimentary definition of it, but it doesn't skip any values along the way. All right, so think about a measuring device. You're going to get that idea across. So like a thermometer to measure temperature. Like if that thermometer goes from 0 degrees Celsius to 100 degrees Celsius, is it going to skip any values along the way? Like if the room starts off at 0 degrees Celsius of freezing and then steadily warms up to boiling, is it going to be like, all right, well, I'm going to skip over every odd number along the way. So at no point from 0 degrees, so from freezing to boiling, would it ever hit an odd temperature? Like, no, it would have to hit every single degree going from 0 to 100, including all the decimal degrees. Right? Same thing with a measuring device to represent weight or length. Just because it doesn't say it on the ruler doesn't mean, like, if I'm actually measuring out, like with a tape measure, start at somebody's heel and work that tape measure out to the very tip of their big toe, I might not take note of every, like, 1/1000th of an inch, but it is being accounted for as that ruler has been expanded, or that tape measure has been expanded. All right? That's what continuous is talking about. But the statistics textbooks, the introductory ones anyway, they like this definition. A random variable that is not made up of countable values. It's like, why? Why do you have to make this so difficult?
Uninterrupted would be better word.
Yeah. I mean, I would even settle for something with, like, random variable that is not only made up of countable values, like made up of every value on an interval from beginning to end without interruption, like anything other than this, but this is what they go with, right? Because the rationale is they're hoping that you'll understand it better by saying, all right, get to know what a discrete random variable is. Continuous is not that. All right? And in a lot of ways that works. So a discrete random variable, countable values, you can determine its value just by looking at it. Right? Just by counting it up, doing the finger pointing test.
So
Right?
it's like the GPS telling you not to turn left.
Right, exactly. And or
Instead of just go straight, don't turn left.
yeah, and I kind of wish GPS has worked that way, where it's like, whatever you do, don't do this. Do anything you want, just don't do this, because I'm looking at, like, I'm pulling out of the 31st Street garage right outside of Madison Square Garden, and I'm seeing that blocked off roadway in front of me, and Waze is telling me that's the way I want to go, and I'm like, that is not the way I want to go. I'm like, Waze, please give me other information.
Tell me what not to do.
Yeah, and it's like, I don't know what to tell you, man. The map is telling us you got to go straight, pal. And I'm like, well, you know what? I'm not gonna. And so I just counted on it rerouting me. I knew I had to get to the other side of that barricade in some way. So I was like, well, I'm gonna go south a little bit and work my way over. But yeah. But yeah, if I needed to know the number of chairs in the classroom, I don't need a ruler, I don't need a stopwatch or anything like that. I just need one of these babies. All right, so you got 1, 2, 3, 4, 5, 6, and so on. All right, number of light bulbs, not really number of anything. All right, that's what we're talking about with discrete random variables. The sides on the die, that particular case was discrete, all right, because you can count up the number of sides on the die. All right, the continuous, again, is just not that. So how do you graph it? Well, honestly, it's going to look very similar regardless of whether the graph is that of a discrete random variable or a continuous random variable. The issue is when we get into probabilities, we're going to have to correct for the fact that sometimes we're going to be using a continuous probability technique to evaluate a discrete random variable and vice versa. All right, so basically, we're going to have to make some adjustments, right? But in order to make those adjustments, we got to learn the ins and outs of each particular type first. So probability distribution for one roll of a fair die, very simple. All I need to do is plot each outcome against its corresponding probability. Now, because all those probabilities are equivalent, that's not going to be difficult at all. Some might say it'd be super easy. Barely an inconvenience. I express myself through my t-shirts, as you have probably undoubtedly already noticed. Which indirectly means I express myself through the thoughts of others. I'm going to give it a corresponding height of 1/6. X represents the individual outcomes, of which there are 6. So what I'm going to do is split this rectangle up into 6 congruent sub-rectangles or sub-intervals. So I have 2. I just need to break those 2 into 3 apiece. So here's autocorrect is our friend. Oh yeah, that's what I meant. The closest I ever got to having students take notes on tablets and, just electronic devices was the semester I didn't give out a note packet. And I was like, all right, here's the deal. I'm going to go paperless. Bring in your own device. Take notes on that. Tell you which app to get. We've got free trials for everyone. It'll get you through the semester. I'm not going to print up note packets. But if you want them, here you go. You can print it up yourself. Class of 38 students. 37 students came in with printed up note packets that they themselves printed up. 1 student came in with a tablet. Like, all right, it's never going to work. So, what can you do? It'll eventually happen. But it'll only happen when all teachers start doing it. Because then it's like, the idea is like, if I'm going to get a tablet, I'm not just going to get a tablet for one class. Like, it's not cheap, So if all my textbooks are going to be on that tablet, all my notes, all my tests, all that stuff, then I'll go that route. But until that day comes, keep giving me handouts, pal. Here's what it is. High school is different. They all have tablets, iPads, phones, Apple Watches, everything. They just don't want to use it for school. You do. So, but that's the graph. Now, if it has fluctuating height, it could be a little bit more of a pain to graph, but this one's not bad. Right? And my bars could be a little bit more congruent, but I don't know. We're not getting style points here. It's just like, did you get the job done? All right. So each one of these has a height of 1/6. Add up each of these heights together, and you'll get a total of 6 out of 6, which is your entire distribution. Right? If the heights of all of your bars are equivalent, then you're looking at something known as a uniform distribution. Very easy to determine probabilities when you're dealing with a uniform distribution, but not everything's going to be the roll of a die, a flip of a coin, and so on. Right? So we have to account for those. So that brings us to the next page, where we look at this situation. And this is what I was saying before. The mu plus or minus 2 sigma is the rule of thumb when it comes to unusual results. I'll take it as a typo though, because the font here got a little messed up. So if somebody wants that or needs it. If you're not sure whether or not you've gotten your bonus typos or typo bonus, check Blackboard, because you should get a total of 3, or will get a total of 3 bonus points, 1 for each unique typo. If you've submitted like 10 and you haven't gotten any bonus points, it's because somebody beat you each of those 10 times. Right? But as people keep reaching the max, then you'll have less and less competition to the point where you'll be like, oh, typo, a race is on. You'll look around and nobody will be picking up their phone. It's because everybody else already has the bonus points. Right? So this data is going in your calculator. We're looking to determine whether getting 13 girls among 14 births is unusual. Right? And we'll talk about what the graph looks like also and stuff like that. But that's where we're starting with. A little background context on this problem, because context is an important characteristic.
this is not, people have asked, this is not one person's children, right? There are 14 births. You got to kind of imagine that you're the nurse in the neonatal. That sounds right.
Prenatal medium.
Yeah, just that environment. Like you're the one that's, taking care of the newborn babies, and
Neonatal care.
neonatal. Okay, so a bunch of babies are there. There's 14 of them. All, some of them maybe have the same parent, but most of them don't. A couple of twins may be involved, but it's not one person who just had 14 kids. Okay, that's the important thing, because people wondered about that. All right.
And I'll talk more about where this information came from and what it means down the line. Something to keep in mind, you can clear out your data sets in your table all in one shot, or you can do it one at a time as needed. Again, if you need to clear out a column, right up to the column heading, hit clear and then enter. Don't hit delete. It's only when you want to clear a single entry in a data set that you hit delete. I hit the wrong thing. All right, so I honestly don't think I can repeat that often enough. People run into that problem all the time, so I'm just going to keep saying it. This one I'm not going to share right now. All right, so the graph here, I mean, if you want to make the graph by hand, that's fine. It's really just more like a, graph it on your calculator kind of graph. Observe the graph and then determine the distribution.
Got points.
Thank you. I appreciate that. That would have saved me from staring awkwardly at the screen, trying to figure out where I went wrong. Again. All right, so how do we create the graph? Well, it is a frequency distribution. Again, whether or not it's a regular ordinary frequency distribution or another kind of frequency distribution, it's still a frequency distribution. All right, so what we could do is create a histogram. I mean, that's what we did for the uniform distribution. It's just all the heights were the same, so it was easy enough to do it by hand. All right, so again, just a refresher, second y equals you're going to select stat plot or plot 1. Turn it on and select the one that looks like a histogram. All right, my interface is different, obviously, because of this coolness that I have here. All right, so select the one that looks like a histogram. It's the one that looks, I believe it's something like this. Yeah, it's straight up like the middle finger, if I remember correctly. Yeah, somebody was having fun when they created the code for this calculator. So there's that, and then make sure that it has L1 and L2. It's referencing those two columns. All right, and then hit zoom stat, zoom 9. For me, I just hit graph and I just start pinching it. Well, I gotta get rid of that too. I don't know if yours came out as gorgeous as mine did. That thing's a work of art. Look at that.
Sorry, you made me laugh. Frequency says one change it to L2.
Yeah, it should be L2, yeah. L1 and L2. How do you zoom out? Oh, it doesn't. Interesting.
Like hardcore.
Oh. And you did zoom 9?
Yeah.
Okay, so then select, well, there's two ways to handle it. So you can do zoom out, but what I would recommend is go into window and what can I, holy moly. Oh, it's just a straight up, yeah. Okay. So, oh, mine's gorgeous. That's terrible. All right. So we got the fix. It's actually very easy. Your x values should encompass the given x values. So your x min should account for these numbers, x min and x max. So let your x min be 0 and your x max be 14. Your y min, your x scale, you can let that be equal to 1 because that's what the intervals are here. It's going by ones. So where it says x SCL, change that to 1. And then y min, y max, make that 0 and 0.21. All right, because the probability can never be less than 0. Right, it can never, it just can't be negative. It also can't be bigger than 1. But the largest probability I have here is 0.21. So there's no need to go any higher than that. So for my y min and y max, make it 0 and 0.21. It doesn't matter what you go by in terms of a y scale. All right. So your x SCL, the one that comes right after your x max, just make that a 1. Then hit graph. Don't hit zoom again. And then yes, yeah, it's a good-looking graph, right? Yeah, very satisfying. That I don't know why that happened. I can't explain it. I'll have to try it on my own calculator and see. But my sense is that it has something to do with the percents, but it typically doesn't happen like that, so. Okay, come on, straighten out, you son of a gun. This really shouldn't matter so much, but it's bothering me with daylight saving. There should be a snap to fit, but it does. It's snapped to fit in the wrong way. All right, well, whatever. All right, so clearly that's not a uniform distribution. Okay, it looks like it's an approximately bell-shaped distribution. It's definitely symmetrical. The suspicion is that it would be a normal distribution. Okay. All right. So what we want to know is whether or not it's unusual to get 13 girls and 14 births. right? So common sense tells us that it's probably unusual. I mean, it depends on how much you believe in the Chinese calendar. The gender calendar. I mean, that baby is spot on, though. I'll tell you that, because if you ever notice, like when people are having kids, it's like, man, like all five of my friends, they're all pregnant and they're all having boys. That's so strange. And then like they're on their second kids like 2 years later, and they're all girls. And it's like, what? I mean, pregnancy packs aside, like how did that happen? You know, like what's the story there? Is there something in the air? Like how does that work? And then you line it up with the Chinese calendar, and you're like, holy crap! It's all like right there. You know, the math is broken down pretty nicely too. Right? So that's probably a different conversation for a different day, but it is a conversation that's worth having. But yeah, so like you've definitely you've experienced situations where you're like, I didn't expect that to happen, but I suppose it can happen. Like my cousin wanted a son. He's got 4 daughters.
Likelihood is.
I mean, he wanted a son after the first daughter, and the second, and the third, and after the fourth, and he still wanted a son. But after that, he's like, I can't take the chance, man. How many weddings am I going to pay for? You know, so it's not. He had nothing wrong with the girls. It's the paying for the weddings. That's what was getting them, right? And so, there's just some people. It's like they could have 13 kids. They're all going to be girls. Why? It's just the way it works.
My uncle has 2 sets of children from his first and second marriage, so it's got 6 kids total. Only one of them is a boy.
Was it the last one?
No, it's the third.
Oh, okay.
And 3 more girls after that.
Yeah, 'cause I always like to know, like when it's a single, when it's just a one boy. I like to know where he falls in the pecking order. That gives you a sense of the mentality of the father.
Yeah, my mom is 1 of 9, and 8 are girls. So, and the oldest is the boy.
And the oldest is the boy. Ah. I'd have to think about that one.
I have an unrelated, is there a reason why it still leaves in mid?
There is not.
Okay.
Now, after you changed your window, did you hit zoom 9 again?
No,
Did-
grab.
You hit graph, huh?
Yeah.
All right, let's take a look real quick. Oh, so in your stat plot, you want to have the frequency as what?
Oh, it was nothing.
It was just a 1.
Okay,
Yeah,
thank you.
no problem. All right, so a lot of different reasons why you could say, hey, 14 births, 13 of them can be girls, but let's see statistically whether or not that should have happened. All right, so unusual, usual, we're talking about mu plus or minus 2 times sigma. All right, so in my calculator, I'm going to do stat, calc, option 1. Well, let me quit out of here first and do it. Stat, calc, option 1, L1, L2, just like before. And it'll give us the mu. Now, again, we are interpreting that X bar in the display. You know what? I'm going to snip this in here. The X bar in the display is going to be our mu. And that's just, unfortunately, something you just have to know. / write down on the note card. This one is our sigma, but that one's the obvious one because it actually has a sigma in it. The x is just saying what the variable is. Sigma sub x is the sigma of the x variable. So 7 plus or minus 2 times about 1.875 but I don't want to work with the rounded form of it. I want to work with the more exact form. Now 7 is fine. We can work with that. So in my home screen, I could do 7 minus 2 times, but then just going back to the first unit, to get these symbols, really any of them, we're living in the vars stat menu. Plus so vars, for me it's option 2, but for you it's option 5. All right, and just find the one that says sigma. All right. Sigma X, that is, because you could also have a sigma Y in there. All right. So run this computation. You get the most exact possible answer. Then feel free to round it after that, but you're not going to run into any rounding issues along the way if you work with the most exact form every step of the way. So we're looking at 3.2498. So really it's 250, comma 10.750. As rounded values go, those are pretty nice. All right. So this is our usual interval. So these are our usual values. So we would conclude that 13 girls in 14 births is statistically unusual. Right. So it's a nice little mathematical justification for what we could expect to be the usual outcomes under a certain circumstance or a certain set of circumstances. So anywhere between 3 1/4 and 7 3/4, 10 3/4. So really, I mean, if you're just thinking in terms of ordinary values, we're talking about anywhere between 4 and 10 is our usual set of values. All right, so 3.2, anything more than 3 or equal to 3.25, but we wouldn't expect it to be a quarter of a value, and less than 10.75. So these are our usuals. All right, so now you can kind of give it the eye test a little bit and say, all right, well, does this make sense? Well, you have 14 births. 7 of them were boys and 7 of them were girls. You'd be like, oh yeah, okay. Just the way we wrote it up in the playbook, I guess. If it were 6 boys and 8 girls, yeah, or the other way around. The other way around is the same. 5 and 9, one way or the other. Okay. 4 and 10. Yep, still reasonable. I mean, it's a little more on the side of like, okay, must be girl season or boy season, you know, depending on which is the more prevalent outcome. But then you get 3 and 11, 2 and 12, 1 and 13, 0 and 14. And it's like, oh, this is getting crazy. What's going on here? You know, they just, like, if you walk into a neonatal unit and you see they said that there were 14 births and you see 14 girls there, you're gonna be like, were there like 14 births in another unit and you just put all the girls here and all the boys there? Like, what happened here? Because this is crazy, you know. So that's the power of this particular concept. You can really start getting at whether something is considered to be usual or unusual. A little background that I was mentioning before. is that I actually got this from a really old textbook, and I'm pretty sure it was made up data. Well, this data is not made up. We'll get to where this information came from. This is actually 100% correct, but not necessarily always relevant. But the actual word problem was a company claims that through a particular medical treatment, they can enhance your chances of having the gender of your choice when you have a child. So they call it a gender selection technique. Okay? And so what they were claiming was that in X number of births, you would have, instead of half of those number being boys and half being girls, you would have, let's say, 3/4 boy and 3/4 of them would be girls. 1/4 would be girls. And so, is that statistically significant in terms of the outcome? And really, all you're looking to determine is that something that could ordinarily happen by chance alone, or is that something that maybe there was some impact there, right? And so that's one of the things that we're going to be focusing on in the remainder of the course is the difference between what would happen due to natural causes and what would happen due to some sort of intervention, right? Because if I tell you that I can guarantee a 5-point increase in your grade in like whatever class, just by following my patented protocol, it's only going to cost you $1,500, like whatever, but statistically, the variation in grades shows that a 5% change in your average could happen just naturally anyway, then I'm charging you for something that would normally happen, regardless of whether or not you did my program, right? So that's really the idea. Honestly, I kind of look at a lot of the material that we learn in this course as an opportunity to see through other people's bullshit.